where we'll take the questions at the end of the session. So just wait for it. Okay, we'll start now. We already have some participants joining. Um, okay, so good afternoon, everyone. Again, on behalf of Hackathon 2026, which is organized a part of Semicon India and all the partners and organizing team, I welcome you all to the knowledge and Q&A series of the Hackathon 2026, again organized as a part of Semicon India. The hackathon is organized by Semi India with our strategy partner ISA, industry partners KLA and Applied Materials, academic partner um, VIT, and implementation partner IFOC. So thank you all for joining today's session. Just a brief background about what Semicon India is. So Semicon India is a premier platform bringing together global semiconductor leaders, companies in industries, innovators, experts for the growth of India's semiconductor ecosystems. And it promotes a collaboration of emerging technologies, opportunities across the complete semiconductor value chain. So we have global partners like Applied Materials, part of this hackathon, who have provided the wonderful problem statement for you guys, which is again a real problem statement associated with the semiconductor domain. And we are trying to get solution from you guys for the same. So today's session is particularly important because this can be a final session for knowledge transfer or explaining your key concept behind the problem statement and given a session for phase one submission, which has the deadline of 16th of August. So we encourage all participants to use this opportunity to clarify your technical questions, validate your approach, and uh, better understand the expected solution and submission requirements. And we sincerely thank you, Applied Materials and team and Ayush sir, for presenting the problem statement explanation in previous session, and today again guiding them on the key concepts and taking on the questions. So today's session will focus on what are the key concepts related to the problem statement. What if you have any questions, you can directly ask and get it clarified. So again, today I like to introduce our today's speaker, Aayush Raina sir. He is senior algorithm manager at Applied Materials. Thank you for Aayush sir joining, and I won't take much time to talk about. I'll give the stage to you to start with the session.
Yes. Thank you, Saurabh. Uh, in the chat, somebody would like to can express like if you want me to present the problem statement again for first 5 minutes and then start it. Somebody who has not joined the last session, say just yes or no. That will basically help us because I will jump on this advanced concept today. Uh, so if do you want me to repeat the problem statement once? Say yes. Okay. Okay. Let's interest of everyone. Let's do that once again. Then quickly we'll rush it. You can if you still have some open questions upon the problem statements, please revisit the previous video. Okay. I'm just trying to give a brief here so that you can understand the next concept which we are talking today. Okay, so what we are trying to say that it's a pure image processing problem. Today we will talk in depth also. And let's say the problem here is like we on a wafer, you see image on right or illustrative example here, you will have a pattern of dies, and in this there is a reference, and over there in reference you grab one image. Then you try to go to another die, and basically you want to grab and the same location another image and see whether the pattern is same. So the one which is marked here star is basically is the actual reference pattern, which we feel like it's a good printed pattern, and we want to make sure that the other dies are also printed equally well. But the wafer is mounted on a stage, and because of some thermal expansion or maybe some vibrations, we don't land up exactly at the same place. We have generally an offset. In this image, it's bigger, but in generally we have a small offset. Uh, so as a result, we miss the basically the target. So we want to recorrect ourselves and reposition ourselves at the right location. So in order to do that, we don't take a high resolution image at the new location. We take a big image here, and in that search this particular target, and then go and take a fresh grab at the revised location, which is at the high resolution. For example, so let's say this pattern, when we will go at a new location, we want to search for this pattern. We will take first a big image zoomed out, and then we find the pattern and we'll go, okay, yes, I have to take a big image at this location, and then I will zoom in and take a hunt. So what we are saying is you have two zoom modes, and one is 100x and one is 10x. So 100x is left side. You have a reference image, which is the star image. You want to find out that image in the bigger area, and then once you find it, you will take an enhanced image. But our aim is in this problem statement is just to find the image. Okay, just find the right location. So more examples. You're trying to find the patterns on the left in a dense view, or maybe a compressed view, or you can say zoom out view on the right side, and you have to find it closer to the center. Okay, so it can be present in many ways, any places. You are supposed to find it closer to the pattern center. So this is what you have in case more than one tile is matching. You find something which is closer to center. I hope problem statement wise we are clear. And in the expected solution, we are expecting that you create a synthetic data set, which is actual like the images which I showed you with DRAM and FinFET style. So these are CPU and memory architectures, which are very close to what we use. And after that, you start adding some noise characteristics. So today session, we will talk about 1 and 2. Okay, and we leave it to you if you want to use a classical or a deep learning method and try to basically report. I would like encourage to people try both methods and see how these methods and learnings will play out. And after that, once you have a method, you try to basically create confusion metrics and try to give us okay, how good is your accuracy. Okay, so for example, um, on the image in the right side, if you find it at a location, you could be 1 pixel wrong or 2 pixel wrong here. Maybe you compress it and find it may be 1 pixel or 2 pixel wrong. And in that case, you have to report how much is your pixel error. Okay, because you will create the image, you know that, okay, what was the right location. And when you place it, we'll come to know, okay, what is how much is the new position, what is the new position here. So you will anyhow give the code for creating the data also to us, so we can recreate the data and we know that, okay, what is your ground truth and what is the image, where exactly it should basically best position, where it can be registered. I'll show more examples today, which will be more clear. Okay, we gave some reference literature to you, which you can use to basically generate data. And I will show you today how I use this literature to create data for today. And I will share my repo also for your cases. Yeah, so I think so. Most of the first part is we should be accurate. Second thing is the computation part. I think so. Most of the challenging part people should focus is that to do it right. Computation time will come. It's like secondary. If it is like, say, both are like one is 1 second, another is 1.2 seconds. For us, both are equal. But if it is like one is 1 second, another one is like 1 minute or 2 minutes or 5 minutes, that is something which is a very heavy network. It is something very costly. So I think so. Computation time, focus on it, but don't over optimize your code. First, focus on accuracy part. Okay, and metric part also I mentioned that you should have this study. We want you to give the study that, okay, if I add noises, how my precision is falling. okay, or accuracy is falling. Generally, the PR curve is something which is standard in such problems, and you should see that how good is my precision when I try to do it. Summation format, I think so it's clear. We will talk more about it if required. But as of now, we want you to focus on right augmentation and then on results. This is something which is key enabler. If you don't have right data to show your value or how good your algorithm is, you will not be able to achieve good results here. Okay, because if you because we will test it on our data also, and I will present the data today like a sample data which I can share, which is doesn't have customer intellectual property, but it is close to what we expect the solutions. Okay, so I guess this is from our side. I will share to Saurabh the scoring part, which Saurav's team will basically help us to evaluate all code, and maybe this utility code you will also get from me. I will place it in the repo. Do we have any questions at this stage? Yes, Senthil is saying, yes, Senthil, we'll talk about it. It's good that you can locate the target, but today you will see the advanced targets. Okay, so let's see. Okay, so whatever I had shared in presentation were very simple cases. They had no noise in it. So today I will be talking about, I placed one repo on for you on this link I will share. This repo contains the slides also, which I will talk about. And also it contains the app. Okay, it contains an app which is you can extend on it, build on it, and try to make more synthetic data. Okay, so today I will talk more about the data synthetic data generation. Let's spend few minutes. Yeah, 16:50. Okay, let's talk 20 minutes, 10, 20, 10 to 15 minutes on synthetic data generation. I want to first tell how we are generating it. It's my approach, and maybe later you can extend it and try to see how is your data on the similar lines or not, because our evaluation data set would be starting at this level, somewhat at this level. Okay, so the problem statement is very clear. You find the recover the position after the navigation strip. You have to, we give you reference and search image, and you have to give us the x and y coordinate closest to the center. Okay, this is sorted. We know that both are 1000 pixel by 1000 pixel. In the zoomed in image, we have 1 nanometer is 1 pixel, 10 nanometers is 1 pixel in the search image. Field of view is same for them. It's computed from the above two. Sorry, field of view is bigger. It's not same. Only the image size is different. So image size is same, and pixel size is different. As a result, the field of view is also different. Okay, so now I try to create some samples based on some calculations. You can read through the document also. It's on, and you will understand more. You can feed it in Gemini or Claude or any Codex, any architecture, and see get more knowledge about it. So I simulated both memory and logic CPU FinFET architectures with different size of the structures. So for example, this is one of the structure. It has, let's say, 2 or 3 layers. Okay, and it has like this is a memory cell, DRAM cell, and this is how it looks by design. And if you see some polygons, we are shrinking, some polygons we are expanding. Okay, and this logic is there in the repo. So if you see now, this will look like your somewhat like this will look like your reference pattern. Ideally, this is not relate. This is not how exactly the pattern looks like, but the structure gray level somewhat is similar to actual patterns which you have we have seen. Okay, so this is a zoomed out image, and now on this area, I'm just cropping randomly. Okay, and so there are many versions on it. We are trying to simulate. I will show in zoom in versions also. You will get to know. So I have created, let's say, some couple of areas, and I will talk about it like how it looks like. So in every area has different resolution. Some of them are 10, some of them are 7, some are 14, 22. So then I can take samples from each area and try to find my pattern there. I'll show you how it works. Okay, this part let's talk about later. So one part which concept which we discussed is like scaling also, like some polygons will appear smaller, bigger, so you can increase, or you should have a method to increase or decrease so that you can play with more data. Uh, so for example, you will have in some of the images, the polygons will be bigger, but on the right side on the image where you have to search, polygons could be of the right size. So how do you, even if you're compressing, you have to account for that scaling part. We'll see more. Uh, there is another aspect in noise which we talked about is like astigmatism. You may get images which are like blurred, and you may have to correct them, which filters you will need to before search in the image. So if you see your image, it can get blurred. This is the math behind it. I guess most of you can read about it, and if you are aware, it's excellent. Some of the noise will be short noise functions. You will add some short noise to it. You can see from the image how it will be look like. The images which are having high dose will have higher short noise compared to the low dose ones. Uh, then yes, this is okay. Then you can also have some angle. This is like some drift and jitter. So how do you account it? This is too much. I would say 1 to 2 degrees. Somebody had asked for rotation. I'll limit it to 1 degree or 2 degree. But I'm just telling these are the stress test. First of all, your algo should work on simple cases, and then you keep on adding stress, and then show me the PR curves, how it looks like. Uh, there could be also the barrel distortion. You don't have to do. This is too complicated. I don't expect in first version. Will not test you, give you that. But yes, you will have some gamma on the right. That means some patterns on the right side on the corners will get collapsed. Then you can have charging artifacts. That means you can have these kind of lines in between, which can interfere in your registration to find the peak. So how do you correct them? Uh, so yes, I guess there could be cases. So now what will be a problem? For example, this is my left image. It is very clear, and this is not actual image. I'm taking a zoomed in area of this one. So if I take one node of it and try to see how this node will look like on the right side, if you see, you will get something like this. It is too bad. So you have to basically work on pre-processing to some extent to register it right. Okay, when you downsample it, you will basically lose out many things. um then yeah, I think so. This more or less I'm done. This is what we expected. So once you add you have low noise, you will have better. Then you keep on adding more and more noise, and then you see how your PR curve is appears. And maybe this chart may not be how you see. You will see in compared to how the one I showed in the initial slide. But I guess most of the things we have covered. Let's see the demo, and then we'll talk more from the demo side. But this is more of a theory. I don't want to talk most theories because it will be very boring. So let's see what we want to do. This is a very excellent utility. You have it in, this may work very slow if you try to do on Hugging Face. So I'll say that try to not to use Hugging Face and try to clone the code. You can clone it, it's public, and try to run it like I'm running it locally on my system. Okay, so let's see what do we have here, and let's see what we can play with. Um, so this is a small case. Let's say if you say that what I have done is first created the entire pattern using this resolution. Okay, very big resolution, very big image. And then I compress this image to this format. And out of that, I have from the original image, I know that this is how my pattern looks like. And then I've added noise to both of them. So let's say in this case, I created first image with 10,000 pixels, this one, instead of 1,000 pixels, and then compressed it 10 times. So I will get an image like this. And from the original image, I will crop in the same area. So I will get something like this. So this part as noisy, but over here it's like still manageable. Now, how much noise I can? This is a classic starting page. At this stage, if I start adding feature scale, how does my image change? Okay, so you will start seeing some changes on the images. Uh, you see, some of the nodes are compressing, some of them are increasing. You can start creating different images, seeing how scales will matter. Uh, Based on different scale, I have some images from the same pattern. It will start rendering them and showing you here. You can see the background code, how the scaling part is handled. Uh, let's zoom refresh again, and the same DRAM 1x version. Let's say I have, let it load please. Yeah, so I have a family of different patterns. Okay, you can have a sample. From the same sample, you can have different patterns. Why it is too slow? Maybe I'm sharing, that's the reason. I'm too slow. Come on. Yeah, so now it gave a different region. So you could, what I'm trying to say here is you can create one master image on the right side and create many reference styles whom you are searching, so that you can have more experiment data to play with. This is one good strategy which you should try. Okay, I can add some noise. Let's say I can add some on this pattern. If I want to add some noise, I can add this pattern and then see how my registration will look like. So if you see now, the image has a lot of noise compared to the original image. Different type of noise are there. You can also have charging effect. So there was a question like, my code is working with regular ML. Is it working with this kind of data? This is also you have to see. Okay, because we will give this kind of evaluation data set, something similar like this to, and on that validation data set you can test, and you will have this data set. I'm making it public for you. You can change, create things, stabilize yourself from this. I'm giving you one augmentation method. Another thing, let's say we want to go back, and in this also you have many things. Let's say you have so many of them. I would like to show you FinFET 14. So if you see how FinFET 14 will look like. So it's like almost like for every, you have let's say 10 variants here. For every variant, you have almost like 10 samples. So you have nearly 100 samples straight away as a baseline. On that, you can create more data, simulate more thing, add noises, and try to create huge data set if you want. Okay. So in this case, let's see over here. This is a different data set, different structure. Now, if I change some sort of a pattern collapse here, see what will happen. Let's make it bigger. So idea here is, if your structure line is very small, let's say it's less than 10 pixels, then what will happen is that line will disappear on this pattern. So you have to account for it. So for example, a line like this, which is so thin, if it is less than 10 nanometer, it will not show here. So how do you account for it? Can your algorithm account for it? Then you have spot size. Like spot size decides how good your resolution is. If my spot size is big, my structures will also look different. You see, they will start looking bigger and blurred. Okay. And can you account for it? Generally, same setting is applicable for it. It's not like that I will add different settings for different. I will try to keep both the images on the similar settings, but I can add some noise models to different one of them. Okay. Uh, there could be acquisition noise. I will refresh it and then we'll do it again. Okay, so let's say I want to add some drift or shear, some angle. So your search image will start having some angle here on the pattern. So you can start seeing those things once you once you deploy it, you will start observing the pixel that, okay, yes, this is how. You can also run some sort of a basic algorithm. Maybe somebody must have done it. So you can run that and see that, okay, what is your registration looks like compared to original one. Okay. So, so if you they see that it predicts this, actual distance is like this, it made a 2 pixel error because of the noise. Okay, so 2 pixel error means it's like 20 nanometers error on the right side image. Okay. This is interesting. You can play with this corner rounding. So you will start seeing more corner roundings on the patterns. On this one, see if you see these patterns will become more corner rounded. And if you run ZNCC again, it will show something. Barrel, I have given here some distortion, but let's say if you add it, your barrel is will show you here in this image. It can be, you can do 1 degree, 2 degree, but it's like I'll say let's keep it out of scope because it is different. You have to do some affine transforms to basically correct it. Okay. Let's say gamma will basically, you will start seeing on the darkness on the right, on the edges. See, it's more sharper, how you want the contrast curve. You can also do a gamma correction in your code as a block, add a block. Okay, yeah, you can add some charging streaks, let's say these lines, which will show some, you can say, which can happen. I'll say refresh it and show, because of the gamma, it's not showing. So this is just a reference. We are not saying that use this code or use this pattern. But this will help you to understand that your algo where it has gaps. Okay. So if you see now in this case, when you are adding some charging streaks, some big lines, intensity 0, sorry, my bad. See, now if you have so many charging streaks in both, and now if I try to do how much is my accuracy, it should drop. See, 1 pixel drop, you start seeing it. This edge is very good. That's the reason why you are getting registration. But if this pattern we are not searching, we've had search in some way smaller pattern, this edge would have lost because of this edge. If this edge was not there, you could have made an error. You can have more salt and pepper noise and speckle noise. It's like you can have this kind of noise. Okay, now it's still registering. So you see how the pattern looks like very nice very nice to look like this actual SEM image, but actually it becomes more challenging to in such cases to do the registration. If you have a very dominant pattern, you will still find the right location. Let's say in this case, intentionally I gave a very big pattern, But I encourage that you don't rely on this pattern, keep it on the corner or somewhere. Like if you take such big pattern, this itself will correct your, but when we will give you the test data, it will not have this big pattern. It will have something different. You can have you can basically play with this to basically have your own pattern. And so if you see, I'm condensing the pad strips now, make it more and more smaller. So in this case, the error is high, but error is high because of the Y, because there was nothing in Y side it was registering to. But how closest to the center you create that is, this could be an data set issue. But X side direction, it did a good job. It was able to find it in within 1 pixel, 1.5 pixel. Okay. So this is something like a base correlation method. You will have to do a step up. You will have to find something more accurate and to sub pixel. And how you do it, we leave it to you to design the pipeline. There are many fields to play with it. I created this for you. Basically you can see how your seed should be, how you want to create your stack, how you want to create the images. You want to compress some, increase some of them, and then you can compare it also with your simulation previous. So you can use this utility to create some sample data. First of all, understand it, how it works, what is there inside, what you can take, what you can ignore, and how you build things on. Because I felt like most of the people, most of the students or participants were thinking like how we can have the data sets. But now I've given you a utility with which you can create almost like the noise levels are almost similar to what we will give. Okay. So now you can focus more on the algorithm side. How would you find my given pattern inside it? Okay. So now let's say I wanted to take some questions. Senthil said, sir, actually with Python script, I'm able to locate the target in search. Is it mandatory for training ML? No, ML is not training. ML means using deep learning model, right? Maybe deep learning model is not basically. If you don't want to work with deep learning model, it's okay. But if somebody can come with deep learning model and fast and it is good, actually it's giving better results or good results, I would encourage it. We would like to see different approach also, because doing all problems with classical ML model could be challenging. So can you please share this PDF? Everything is shared. I will paste it here, the link. No. Hmm. Okay, I think so most of you must have searched it also by now. So slides are also there in the slides folder. Uh, Sir, missed last session. Whether okay, this sort of is already answered. Well, share with it. On which platform we can simulate this project. You can do it on local. You can do it on your local. Like I'm also running it on local, right? It's a Python program running on Streamlit. You can do it. It's not so complicated, Gungun. Uh, can we reuse retrain models? Can we use pre-trained models? Okay, Ganesh is asking. Yes, you can use pre-trained models. You can use Dino V2 kind of models. You also gave data set. No, this data set is not for evaluation. I think so. What we want to say, when you are creating a data set, let's say I'm asking 30 images from you, 30 data set. For every image, you have to tell what pairs you generated. So let's say this pattern, let's say one category could be you can divide your data set. Let's say I added stigmatism to my data. How my images will look like with that. Okay, this is one area. Then you can add similar way, you can add many options like I was showing here in the images. These are your one of the reference point. Like some of them you added astigmatism, some of them you did add gamma, some of them you add speckle noise. But at the end, if every image is looking same, your anchor, your both left and right images are looking same, it is not uniqueness. You will have to create unique patterns. Like I created some unique patterns in the slides initially, then I created some more unique patterns. We would like to see how you read and create data. Can you generate data? And anyone who is working on algorithm problems should understand how to create data also. What is right data for an algorithm? Where to basically test it, like whether it will work or when it will fail. This is very important. If you just show cases which are very simple and algorithm can solve it, and it fails on the cases which we will give, it will not make sense, because it is just tuned to your approach or tuned to your data. Okay, so be very creative in terms of data. We're giving just a platform, some tools to play with it. But underlying how the patterns should look like is we leave it to you. That is your creativity. How you want to add the noise, how close you want to put it. How would you challenge somebody that okay, I have a repeated pattern in many areas, but this is my place, and it has this for every image. You should be able to explain that why this is a good pattern to search and against something very normal. If you can give that kind of answers for at least some samples of what you are sharing, it makes good. We would like to have a showcase that how good images students have created using augmentation. Okay, this is our goal. That's the reason why we are giving you all tools for it. Okay, then sir, do we have to create a web app for demonstration simulator? No. You don't have to give. You have to just for every data set images you're creating, you will have some with the images, you will have some metadata which is explaining, or maybe you can have one common some kind of a HTML slide like I was showing, which explains every 30 slides, maybe 30 data set, like what is so unique about this pair, let's say reference and the search pair, and how are the what exactly you did for every slide. So every basically every pair that will basically help us to understand that how challenging cases your algorithm can solve. Okay, then the question comes, and until does always search image will have a defect? Always search. There is no defect as such, but yes, the search image. For example, let's say in general, let's say if you are focusing on something very far, okay, and there is a point, there is some object in between, you may lose the focus on background. For example, if you see this is the image, on this the focus will go on the first, this is the most prominent pattern. In this case, there could be a prominent pattern which is more bigger. Focus may go here. As a result, these tiles will get noisy. If you see, these will get noisy. Just like normal camera, like you have, it will try to focus on areas which are more prominent or more Z direction. It has more lift. So they will basically, you will get some areas in background and you will have more noise in them. So as a result, the search image, you should expect the search image would be noisy. Because we assume that something which is taken at a very close shot, you don't expect too much noise in it. But on this one, we expect noise. You can add noise on this, it's good. That is, maybe it's an imaging issue. But in this case, since the resolution of structures has be so small, you will tend to have more noise, because when you can say electrons are falling, you will have distortion, you will have short noises coming in. And then you can also have a scaling issue because of how the data is collected back. from when the electrons fall on. So you can read something about it that will give also some idea that okay, how these noise models work on SEM images. Web app, no, this is not required, Gaurav. PDF, late to the meeting, how to get the information. Okay, so you will have recording. So the images you gave are drawn DRAM style, but not looking real image. But do we have to image same real image? Senthil, I think so. What you have asked, if you see down, this is adding this kind of noise will make it closer to same image. So this is how it looks like more. Okay, the example which we started may not be very clear, but so now the ones with these, you can say this package, you can create something like this. Okay, why do you, sorry, you don't know. When you say highly periodic region, do you expect a reference to have multiple visually identical candidates, or should there be always a subtle distinguishing feature? See, some cases you can add a periodic pattern. For example, in the image which I showed you, let's assume this is the right pattern from where it has been drawn. Somewhere on this pattern, no, this is more or less unique, but maybe if there was a line here, it could have registered in, let's say, this pattern also, somewhere here, if it was something on this side, because both of them have a similar, I can say, density ratio packed. But what we expect in those cases is like your algorithm will somehow know that am I close to center and try to pick closer to center. We are saying for simplification to find it close to center, but in future maybe we'll be giving it with respect to point K. So point K could be anywhere, but for this hackathon, we are saying to make it closer to center, simplifying it. Okay, so you gave us the tile which is closest to the matching to the center. Maybe this pattern is present here, on top right, everywhere, but it's selected here. I'm not sure why. Maybe the right place could be here. Okay, which is more closer to the center. Where accuracy would be calculated to reference bounding coordinate. Also, is their ideal data set size? Um, Reference to bounding box coordinate accuracy will, yes. If you see, accuracy should be always, you are the creating data. You are the one who is creating. So let's say if I say what is my ground truth, I know from where my search image from where this image has been taken, because I created a bigger image first and then compressed it down, and from the bigger image I have cropped the area, so I know from where I've cropped this area, and then I have condensed it, added noises, and then try to figure it. So we have given you an approach. This is one of the approach. Like I create, instead of creating 1000 by 1000 image, I create this image as 10,000 by 10,000, and then grab a part of it like this, which is on left, and then reduce it 10 times. So then I will have the image like this and an image on this, and then I have to search this and this side is. So it becomes much more, you're very sure that where your ground truth was, from where you have cropped. This is one way of doing it. You can try many other ways. I'm trying to help you with some which is like bottlenecks, or maybe some small things which are limiting you to the focus on the main problem. So these things will help you to focus on the core problem, on the algorithm side, not on you're not stuck on the data set. So now you at least you have a starting point with which you can create data sets, and you can focus on the problem part. uh, Sir, can you explain confusion metric at 1 to 5? Is it difference from the ground to top left point or to the predicted top left point? Hmm. Okay, well, let me check the problem statement. Like where in the statement where we said yes, 0 0 is top left. Okay, so yes, so what we say 1 to 5 pixel accuracy. So let's say you have a data set, and for which you had a image pair left and right, for which you add a ground truth, and then for every image you are adding, let's say, a case, you are adding more noise to it. So what, as soon as you will keep on adding noise, we would like to see how good is your algorithm accuracy. Does it know how to denoise it? For example, this is a chart. So we expect that when your noise levels are very low, okay, then at that time you will be very closer to where the actual ground truth was. You will be able to find the location. But as soon as you start adding more and more noise to it, the functions which we are given, the examples, you will start make your algorithm may start adding some errors. Okay, maybe 1 pixel, 2 pixel, like we were seeing right now. So we expect that it should fall. And but if you can denoise it and still maintain a high good PR curve, then it's nice. But how much error you can make? So let's say if it's 1 pixel, you will make 10 nanometers error because 1 pixel on the right image is 10 nanometer on this image. So if you register 1 pixel right, you already have made a 10 nanometer error. If you make 1 to 5 pixel, then 5 pixel, that means 50 nanometer error has come. So this image, it's like almost like 50 pixels you are registering at the wrong location. When we'll go and take an image, ideally in ideal case, we will have some error there. So in a nutshell, in a summary, I'll say that you try to add noise, make edges so blurred that you can have a problem to basically solve that, okay, you have nearly 4 or 5 pixels on this image where the algorithm can go wrong. So that we can see how much error you have made. But it's just a range. Okay. It's not like you have to create a data set which has, you have to create a case where your algorithm shows 5 pixel error. If your algorithm is good, it will not make 5 pixel error. It will stay between 1 to 2 or 3. Okay. I think the terminologies wise, you may be confusing, but when you will work with and try to read about it, it's a very interesting problem to solve. And it's not like that you cannot solve it. Like people have asking me questions, I feel like they've already solved some base version. So others can also do it. Yes. So, but the evaluation said 1 pixel cut of high confidence score. So what we will say is like Bhaskar is saying. Yes, you're right, Bhaskar. So when I say that you are making 3 pixel error, but my cutoff is like 1 pixel. How you do it on 1 pixel? How you do it on 2 pixel? How do you do on 3 pixel? That will help me to evaluate that, okay, Bhaskar, your algorithm, how robust it is. Even if I give a noisy image, you can still do better on 1 pixel error. Sir, can you please create show us optical microscope images RGB? We'll have to create those for you, Mandeep. And we have images, but those are customer images. So you can search on Google also. Not sure. I should try searching it. Did you try search in Google? I think so. There will be some images. Something like you can expect something like this. This is a good starting point. You can search for related images. This is also one good image. But this is simulated. Ideally, it will look like this one, this one. Okay, such patterns. This is very zoomed out. Yeah, and this is like very zoomed out. And open these links. But it's like you will have some small pattern which you want to search, and yeah, this is a very big image in which you are searching it. So yes, so you can have a look like this on internet and try to see can you create synthetically also such images. Mandeep is maybe it's like a good place to start, but ideally you will not have this resolution. You will have very these will collapse. Like this is very you can say very clear case. Okay, but on the right side when I say the image, I feel like it can register to it. It is a RGB part, but how did you achieve it? Because to me everything looks same. Like how did it find it? Because it's so much repetitive nature here, and and plus the structure size is not justified. Like it's in you will have some images like in OM the way I showed you. It's like there's a difference between two microscopes, and so you will see more better circuits and something like this. Okay. Um, Bhaskar, I don't think so. Like the test data set, let's assume at this stage for the evaluation, we will guarantee that at least 80% or 90% of the data, 80% at least you will have to register, you will get to for registration. Okay. It's not like you can we expect that this if the pattern is there, then only it will basically you can get registration as the score will be very poor. Sir, what should be the ideal data set size? As I said, it's depend upon your algorithm. You decide. You are the owner of your problem. You decide that okay, I have to test this. My algo. I have some approach in mind. I will test these cases. I will have repeated patterns. I will add this size polygons. I will try to make my shape, which will I will make them structures, let's say, so small that they will not appear on the right side. How will I search it? Can I add some pattern which can affect my algorithm in and create nuisance, misregister or not with existing algorithm can challenge. You can challenge the algorithm approach via AI tools and ask itself that okay why it will fail, in what cases it will fail. Make data sets around that. Try to make it fail, then fix it and justify that data set. Okay, yes, this is a data set which this image pair had this problem and I overcome it in my algorithm. Such cases are also handled in my approach. That is the right way of approaching a machine learning problem. So we it will not always happen that we have one data set and we have a clear problem to solve. So we will give, as I said, as we committed earlier that we had given data sets. I will try to request team members to basically see if we can generate something OM also for you. But as of now, I feel like this is a very good starting point for you to start. Okay. How will you test on dataset if we train model on our dataset? No, the format is same, right? The image is same. So your image, I'm giving you one reference. I'm giving you search image pair, and I'm telling you that this is my ground truth. What as per your algo is the ground truth? If you spot on match on that, then we can compare you can say the difference and see that okay, how good are you on the pixel level error? Okay. So Gaurav, I think so it's clear, right? It's like you are creating two images. You're testing your algorithm or model. You create your model or algorithm to turn two images, right? We are also giving you two images with this input. We are giving you this input, okay. And with that, I can compute the predicted versus actual. I get the difference. With that, I can come, okay, how much error is coming. Okay. Um, See, it's when I'm sharing this data to you, the idea here is it will help you. Uh, not don't feel like don't feel like it's very complicated. It's like you are getting enriched with this information. Now, most of the overhead which you had till 16th was to create data. This will basically save you some days, and you can focus more on right solution. Okay, so see it as an input from our side that it's helping you to basically show progress faster on the solution side and evaluation side. What else I had in mind? Yes, I wanted to cover some questions which was given to me. So in the 10x zoom ratio between reference and image always had 10x in the actual data. Could it be slightly 9 to 11? Yes, very relevant. As we said, you can have a scaling or you can have a distortion which can basically slightly vary to simulate the real optical, not optical in this case, SEM, but it's not a drift, but it is more on scaling. A polygon is scaling or up or down. Okay. What is expected accuracy between the actual location and a search image location found by train model? So accuracy would be like not, we will range it between 1 to 5 pixels, see where you fall, where your algorithm falls. And let's say we start with very liberal approach. Okay, with 5 pixel error, how many cases do you pass? If you pass all of them, very good. We'll reduce it by 4 pixel. See how many of them passes, then we make it 2 pixels, 1 pixel, and then subpixel. How many are they passing? So this curve will help us to see where actually. So let's say there could be some. If I keep it, let's say 5 pixel for all, there could be some people who are doing subpixel also. So they should be getting rewarded more. So and on the similar lines, if I make it very strict, everybody will start failing. It may happen that if I say it's 0.5 pixel, only one or two sets a corner cases are passing and others are failing. So that's the reason why we have given a range of 1 to 5 pixel that basically will respect entire audience, and we'll come to know where most of the spectrum is lying, that how the solutions are positioned, which solutions are giving better accuracy and which are giving in terms of. So this gives a wide range to evaluate to everyone, and it's a fair evaluation. Does having more data set count as a plus point because we have more data set? Ask 30. As I said, more data set you have, it's good for you. You can have hundreds of samples like the way we have given. See which data set you will get more marks. So see why that data set of that image pair, when I say data set, is like one image pair, what you have done differently in that image data set, which brings it very challenging for to solve by others. Okay, so this way, if you create 30 sets, those 30 sets will be actually very good to evaluate on them. But every image should have, first of all, like from visually we can see how it looks. But you should basically tell that what actually how you created that image, what was the process behind it. If you have that in for every image or data set, metadata to that, that is the right way to get evaluated for the data sets part. I have a doubt in dataset or patterns are always highly periodic. FinFET may not be, but the image you will see generally it may have some cells or some nodes which will look like periodic. Because in FinFET also you have repeating structures, and DRAM also you have repeating structures. You can read more about them, how FinFET or DRAM nodes appear. So you will have transistors. Uh, PMOS and CMOS. So it will basically NMOS and PMOS, and so you will see basically how in pairs the structures repeat. Same for DRAM, you have cells, how cells will repeat. So that's the reason why we generally say it's periodic, and that's where you have to find some pattern on the corner to basically register it right. Like we had a pattern here. If we don't have this pattern here, so then it becomes hard for you to register, because if I give something here, it can register here, 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 many places. And then in that case, you have to register nearest to the center. So you will arrange it somewhere here, which is very close to the center. Okay. Uh, what is the expected accuracy? No, sorry, this I've done. What is localization tolerance defined as a correct position, a prediction? I guess this we have already covered in terms of pixel error. You should, does that include rotation slide scale beyond the stated 10x ratio? It may have 1 or 2 degree rotation. It can have scale as we shared today. I have a doubt in time complexity. I solve the problem with the time complexity of and log, okay, log CPU. Maybe you are doing NC's cross correlation and you will use GP parallelism so that time execute reduces will considerable approach. I think so. Time complexity is a secondary thing. You have better ways to do it. You should basically read more about it. This is also a welcome approach, CPU. But first metric I'm again saying will be in terms of pixel level accuracy. Okay. Um, okay. Yes, I think so. CSV, we have a slide. This slide was shared to you. This is how your CSV will look like. Wide search image path, this path, GT and GTY. This is how you should have CSV, and you should have output GTX and GTY, output Y and output X and output Y. And you can give that output, and after that you can create confusion matrix. This utility we will give you. Okay, it's very small utility. I will post it in the same repo, which utility you can use, and everybody will have same format. It will help Saurav's team also to evaluate in a fair manner. So suppose a reference images matches with two. Sorry, I missed this, Gaurav. Sir, it's image. Ajay, so if it matches, it's good case. Don't scrap it out again. Try to basically make sure that it is closer to the center. The one you are catching is closer to the center. Okay. It can happen, Ajay. This is okay. It can happen more than two places also. Okay. That's it. I think so. I have covered all the questions. I'm sending here the link to the My Hugging Face repo. Please go over it. There could be bugs in repo. I accept it and let me know if there are bugs. We can correct it. However, at this stage, it's very explanatory. You can go over the repo, try to play with it, try to learn from it. Okay, and it will surely help for you. Okay.
Yeah.
If you
Yeah.
need
Thank
more sessions or maybe some more help, ask Saurav. We'll see what best we can do. But I think so. If we have one more session, we will solve the problem also with you, which I don't want.
you. Yeah.
Because I've already solved some part of it for you in this
Yeah.
session. So
Yeah.
it will not be fair to the other team which is solving different channels. So we wanted you to be engaged in this problem statement. That's the reason why we wanted to assist you with the dataset creation so that it doesn't become a limiter to you to attempt this problem.
Yeah. Actually. So now they have ample time to 10, 12 days to work on the solution and come up with the good solution. What are the requirements have been mentioned to be fulfilled. Regarding the CSV, so they can add the CSV in the GitHub repository. I hope that's okay.
Right. I
Yes.
will give the scoring utility code also to Saurav, and Saurav, probably next week also we will try to give some evaluation method which is like closer to your 16th timeline. So
Yeah, yeah, yeah. Okay.
yeah.
Yeah, we'll have a discussion on that. Yeah. Yes. Yeah. And whatever other
Okay.
questions are, we'll take
Yeah.
it. Okay.
Gaurav, it's you know by now the end of the session what is easy, what is medium, and what is hard, right? If your algorithm is passing on it, it's easy. If it is not passing, it's medium, or if it doesn't have a clue at all that okay where it to register, it's hard. Mandeep, it's in the same Hugging repository. The PPT is there. The slide section, what I talked about. There is a previous PPT which we've already shared to Saurav, and he must have shared it with you all guys.
Yeah, it is made available on the landing page. So check it thoroughly. Also, when you register, you get an email with all the details. So
Yeah.
all
So
details are there
yeah.
on the landing page under the problem statement. You
So
have
this
download
yeah
section here.
yeah. So I was able to make this utility yesterday night. You'll see most of the comments were all 10 last night only. And what I'm trying to say to you, you have immense power from the coding tools at your disposal. Try them, work with them, learn with them. This is not, it's only a few hours of job and it brings you to a level. I understand there is experience also involved, but what I'm saying is within 12 days, you can accomplish much more and you try to aim for checkbox all the items which we have mentioned in the evaluation.
Yeah. And
Okay.
we will also share the current PPT, right, sir? Uh, so
The current
what is your
PPT, what do you,
uh,
the
the
the current PPT in the link which I have shared, it contains a slides folder and the
okay,
repo side, and that index HTML is there.
okay.
Okay.
We will copy the link and keep it for the reference. We will add it to landing page.
Yes.
Yeah. All right. So again, thank you, Ayush sir, for answering all the questions, explaining the problem statement again, and
Yeah.
like helping students to go on the right path, almost solving the problem for them. And
Yeah. Please
I see
thumbs
that
up.
you enjoy doing it.
Yeah. Please thumbs up if you understood most of it, and
Yeah.
that will give us confidence that okay, yes, this session was useful to you. Okay. Good. Thank you all.
Thank you. Okay. So, dear participants, so like, please use the insights shared today, review problem statement, all technicalities, build your solution, and don't wait for the last day to submit. Try to submit as early as possible before the deadline. So make sure so that makes sure that your solution is submitted on the time and accurately submitted. So check all the links, check all the your repositories, make sure it contains all the requirements as stated. Yeah, and the session recording will be made available on the landing page. Also, go check. We have a webinar section mentioned in the landing page where you will see the previous webinars. Also, once this meeting is over, it will also be made available on the landing page. Also, you will receive an email for the recording. So again, on behalf of all the organizing team, SEMI, ISA, Applied Materials, KLA, VIT, and I4C, I express sincere gratitude to Ayush sir and Applied Materials team for supporting the participants throughout the hackathon. We have more journey to cover of this hackathon.
Yes.
And thank you everyone to uh, actively participating in the Q&A session, asking good questions, participating in the hackathon. Most important, because this is kind of a national level opportunity to you to apply your knowledge, learn some skills of the like the prominent industry of semiconductor, showcase your skills during the grand finale. Yeah, that's it.
Good luck then,
Thank
guys.
you.
Hope for the best. Thanks, Saurav, for arranging it.
Good evening.
Yeah.
Uh,
Thank you. Bye
Have
bye.
a great evening. Thank you. Thank you so much.
You guys too. Bye.